on this, I had a certain amount of tolerance, but yet I was intolerant on this moment of inertia lab. So when the whole point of a lab, listen to me, is not to write down numbers. The point of a lab is to convey information, okay? And ideally, at some point, you would have shown me like one complete set of calculations, okay? Didn't necessarily see all, but at least one set. And then on your experimental error of disturbingly large number, you just wrote down the percentages. I have no idea how you did them. I don't know if you subtracted right or wrong. Some of you did, some of you wrote it all out, and it was beautiful, okay? If you just write down that percentage of error, I have no idea how you calculate it. I don't know if you did it right. I don't know if you divided by the accepted value. I don't know if you divided by the theoretical value. I got nothing, okay? So you didn't even show me like one calculation. So that was the source of frustration. But all in all, the labs went well. Other than that little point of contention when I really wanted to scream and yell. I feel like
That's him screaming.
Oh, yeah. Does this mean more massive? Like a very.
Yes. A is larger than.
What? Well, it says mass A is larger.
Yeah.
Does that mean in mass terms or in terms of like size? You know.
Boom.
I guess, bro. I guess.
Oh,
What'd you get?
What is that? What time is that?
Ooh. Oh.
What time is it? Ah, you suck.
You suck.
Take it down. Can we see Vitor scores?
Can we?
No. We gotta compare.
Shoot.
Which one do you need?
What?
I have a question on the work.
Okay.
Number 10.
What's number 10?
It's the mass slides down an inclined plane at a constant velocity.
So,
How much work is done by friction?
so since you're at a constant velocity, let's say, I'm just going to make up a
friction
number.
and parallel is equal.
All right. So let's chit chat about a couple of these problems. So let's start even with like number 1. This is what I tried to show you yesterday with the mass hanging down. So here's what I want you to see is that, and this is going to be important even on today's assignment. When you lift something up, okay, and you make that thing swing in an arc like this, okay, what's going to create that change in that potential energy is going to be that change in the height. It isn't going to be the arc length, okay? It's going to be what that change in height is going to be. Because UG is mgh. So delta UG is going to be mg delta h. So I can either lift this straight up, say 10 centimeters, or I can lift it in an arc where it ends up 10 centimeters above. The energy doesn't make any difference, okay? It's still a certain amount of change in energy that's going to take place. So what that means is that if I lift this thing straight up and let go of it, it's going to hit with a certain amount of vertical velocity. If I lift it up here and let go of it, it's going to hit with the same vertical velocity as when this came straight down, okay? So energy is a scalar quantity.
You mean the horizontal velocity?
Yeah, so the horizontal velocity here
Is the same as
the vertical velocity here, because that kinetic energy that it's going to have is just going to be 1/2 mv squared. So it's either a vertical velocity if it falls down that height, or it's a horizontal velocity if it comes in this way. Doesn't make any difference. It's the exact same value because it's a scalar quantity. So when you get to that question on C where it says, would the velocity of the ball have changed if the ball was dropped straight down? It would be the exact same. The direction would be different, but since you're only going to have a certain amount of potential energy to start with, that's the same amount of kinetic energy that you have at the bottom. So it's just like, hey, I want to go from here to Chicago. Okay, option number 1, I fly from here to St. Louis, I fly from St. Louis to Chicago. Situation number 2, I just drive through Kansas City, and then I end up in Chicago. Situation number 3, I fly from here to Denver, Denver to Chicago. In both situations, where do I end up?
Chicago.
Chicago. Okay? How I get there doesn't matter. I still have the same net change in my energy. Okay? So whether I lift it up, whether I let it come down like this, doesn't make any difference. Okay? When you get to number 11, because if your answer to 11A is wrong, everything is going to be wrong. So your answer to 11A should be something times 10 to the 8th joules. Okay?
And then you said a lot of them are the same, right?
Yes.
Okay, cool.
I did.
They're like roughly double A.
What?
They're like roughly double the value of A.
They should be the same.
What?
Ooh, they should be the same. He said this yesterday.
Wait, A and B are the same?
Yes.
Why are you doubling?
And C is the same?
Yes.
And E and F? Or just E?
E is the same.
What did I do?
I don't know what you did.
You got
really.
A wrong then, since B, C, and
Is A between 2 and 3?
Yeah, times 10 to the 8th. Yes.
you
So
put
your
all of
answer
them
to
wrong
A should be
then.
2.5 times 10 to the
You
8th.
shouldn't
joules.
have to do any calculations for like B or C.
Because you're finding the work.
Yeah.
The work is equal to the change in the kinetic energy.
Okay.
And then the final kinetic energy. So work equals change in kinetic energy, which is K minus K naught. What's your initial kinetic energy?
Huh?
What's your initial kinetic energy of the train?
0.
So work is the same as your change in the kinetic energy, which is the same as your final kinetic energy.
Okay. What I did was I found the acceleration that the jet engine did. and
Wrong.
Don't,
I
Why are you
found the
doing
velocity that did, and then multiply it by.
Don't.
I'll do that.
don't. You
I
made
don't know
it so
what I did.
horribly difficult.
Why are you multiplying velocity?
You haven't even done the assignment, Pop. Shut up.
Oh, so you can use K equals 1/2. You use that.
Yeah.
Oh, that because it's 1/2 mv. Okay, I got it.
There you
Cool.
go.
That's what I was missing. I screwed that up on the other assignment too.
Okay.
Great.
Anyway,
Said anyway.
your answer to number 12, that distance should be between 70 and 80 meters.
I was wondering why I was so even.
On the book problems on number 8, that velocity in meters per second should be around 30. On number 12, this is just a number. You decide if it's positive or negative. That answer should be between 8 and 900 joules.
I know I haven't finished that.
Are we good?
That's why.
Anything else?
Number
NASA
7,
is Archer.
On which one?
the page.
Huh?
Your number.
My number 7?
Is the greater acceleration.
Okay.
What's over there?
Yes, it is.
So Jackson had asked about this. So visualize this.
Yeah.
You got a big car
You just messed it up. I'm just.
Okay,
You had
and you got a small car.
Right.
Big mass, small mass, right? Do they have the same kinetic energy?
This one.
So which one's going faster?
The smaller one.
Smaller one, right? So this one's going slower, and that's v squared, and there's a 1/2 in there for good measure, right? So 1/2 big mass times little v squared equals 1/2 small mass big V squared, right? So let's just pick up a number. Let's say that's 10 joules. I don't care, let's call it 10 joules. Pick a number. So what's the final kinetic energy of each car going to be?
10 joules.
No,
Zero.
0. The final, because they're going to be brought to a stop.
Oh, which question is this?
Number 7.
Okay, gotcha.
On
Oh,
mine.
the distance?
Huh?
The distance one?
Yeah. Okay. So are they both going to undergo the same change in the kinetic energy?
Yes.
Yes. Right? In this case, it would be negative 10 joules. Right? Negative 10 joules. How much work was done on each car?
More
Do not make this difficult.
the same.
Yeah, because work equals
Changing.
change in kinetic energy. So the work is the same. Now, what does work equal?
Mass,
Force times,
distance.
is the force the same?
Cool.
Now, are the accelerations the same? Oh, no, the accelerations aren't. Okay? That's why you have to keep in mind, is it the same force over the same time, or is it the same force over the same distance? Because it's two completely different things. Okay? Two completely different things. Does that answer your question, Vanessa?
Yes.
Okay.
Cool.
All right. Louis?
It. Oh, it's okay. I'll ask you at the end of class. Cool.
Okay. Anything else? Once, twice? So? Okay.
Oh, wow.
I'll go straight into it.
Get into it.
You need the book.
Which one are you? You want 1 through 7?
Here.
Are you in the book?
The book's right here, though.
Cool. So it's 1 through 7. We already
So
did
this
this.
is the 11 letter.
I was gonna say, we did it on last time.
1, 2, 3, 4, 5, 6.
Okay.
What? Okay, cool. So maybe we get 11. Like what we got. Because I was confused on that. That's what I was
11.
That's all. This is 73.
Good.
Good.
Yeah.
Okay. So imagine this. So what we're going to get into today is more of this idea that momentum, or excuse me, that energy has to be conserved. So here's the situation. I'm going to start with a ball, and I'm going to hold it 2 meters above the ground, and it's going to have a mass of 0.5 kilogram. I'm going to hold the ball up here, I'm going to drop it. Okay? And so what I want to look at is what's going to happen to the potential energy as it falls and the kinetic energy as it falls. Now, what I did is I set up this chart. I cannot recommend this chart enough because it's going to force you to keep everything organized. Okay? Now, eventually, we're only going to be dealing with KT and UG. Eventually, you're going to have KR involved. Eventually, you're going to have springs involved. Okay?
Yeah.
So the sooner you kind of get used to this mindset, the better off you're going to be. Okay? So if you don't want to do this chart, that's completely up to you. You all are big people. But I'm going to tell you this right now. If you don't do the chart and your answers are wrong, if you think I'm going to waste 1 second of my life trying to sort through a bunch of random numbers, I'm going to tell you right now, it is not going to happen. Okay? So if you don't want to draw the chart, that's up to you. You all are big people. Okay? But here's the decision I'm going to make. If I don't see the chart and the first thing that's wrong, I quit grading. Gone. Not going to waste my time. Okay? That's just the reality. So I want everybody to be aware of this situation. If you look at my answer keys, I've got charts. You know why?
Because they work.
They work. Okay? And eliminates mistakes. And if you choose not to, fine. Great. But that's going to be the decision that I'm going to make as well. So here's the deal. So right now, nothing's going to be spinning. So I don't have to worry about any rotational energy. For now, I don't have to worry about any springs involved. Okay? Tomorrow we'll worry about springs. Okay? So for now, we're just going to worry about kinetic and UG. So when this thing is up here at the top, what's the only form of energy that it has?
Potential.
Potential. It's just UG, right? Okay? So what do I have to calculate UG?
MGA.
mgh, right? So I got 0.5 kilograms, there's my mass, times g, times 2 meters. So when you do that, what do you get?
9.8.
9.8 joules, okay? So up at the top, all I have is UG. Up at the top, how much kinetic energy do I have?
0.
0. I have no kinetic energy. OJ, if you're a juice fan, okay? It's OJ. I have no juice, okay? It's just sitting up there. The only thing I have is potential energy. Now, if you're a visual kind of person, in this situation, we're going to have two containers. We're going to have UG, and we're going to have KT. Those are our two containers. Eventually, we'll have 3 containers. Eventually, we'll have 4 containers. Now, this is just a 2-container problem, okay?
Those.
So, what we're saying is that our UG container is filled up to the 9.8 joule line, okay? That's where we're at. My kinetic energy container is empty. Now, as I'm going to drop this. So what's going to happen to my kinetic energy as it falls?
Increase.
It's going to increase. Why?
These potentials, it's, I don't know how to explain it. Yeah. Potential's turning kinetic.
Okay, that's one way to figure it out, right? My potential energy is changing into kinetic energy. So we're siphoning energy from the UG to the kinetic, right? Now, from a velocity standpoint, why is my kinetic energy increasing?
Velocity increasing.
Yeah, you're falling faster and faster and faster, okay? So there's 2 ways to understand why your kinetic energy is increasing. What Pop said, UG is changing into kinetic. From a kinematic standpoint, my velocity is increasing because it's accelerating, okay? Now, here's the whole crux of this problem. At some point, you're going to add these numbers together. I don't have KR, I don't have us, I don't have any of that to worry about. So the magic number here is going to be 9.8 joules. So what that means is at any point along the way, this is how much energy I bring to the system, 9.8 joules. Okay, that's it. It's going to be 9.8 joules. I can't have more than that. I can never go to 11, 12, something like that. 9.8, that's the magic number. Now, I don't want you to think that, oh, every problem is 9.8 joules, okay? It's not, because if I only hold this thing up to a height of 1 meter, that's going to have a completely different number. If I take Hank and lift Hank up to a height of 2 meters, that's going to be a completely different number. But what is the same is the concept that when you start up there and you're just holding it, you have no kinetic energy. It's just at rest. I'm going to drop it. So when it gets to the bottom, how much UG do I have when it hits the bottom? 0. Why? What goes to 0? My height. I have no height. I have no UG. But everything still has to add up to 9.8 joules. So, how much kinetic energy do I have then?
9.8.
9.8 joules. Okay?
Just a pretend.
Yep.
So when it hits the ground, does it have potential energy?
No.
Like
Because the
equal to
H
that?
goes to 0. Now, it'll have potential energy stored in the deformation of the ball.
Yeah.
Okay, but that's not what we're worried about.
Okay.
Yeah, you're right, because if it didn't, it wouldn't bounce back. Okay? But then you get into thermal energy, and that's going to get weird. Now, here's the deal. I want to find the velocity at impact, right? Now, I know how much kinetic energy that it has. I know that my kinetic energy equals 9.8 joules. True? Go with this, right? And that equals 1/2 mv squared. So I need to solve that for velocity. So Jackson, how am I gonna get velocity by itself?
You're gonna multiply it by 2 and divide by mass.
And then,
Square root of that.
yeah. So my velocity is gonna equal the square root of 2 times my kinetic energy divided by my mass. So in this case, take 2 times, somebody take 2 times 9.8 joules, and then divide that by the mass of half a kilogram. And then take the square root of that.
6.26.
What'd you get?
6.26.
6.26 meters per second. Okay? Now, I want you to all to pretend that this problem doesn't exist. It's gone. It's gone. It's gone. We're getting ready for the very first acceleration test. Oh, and you're like going, oh, back in the
That's
day.
too far back.
Oh, back. At the time you're like, oh my God, this is so tough. And you're like, oh, really? Okay.
Miss those days.
I know. So you're getting ready for the kinematic test. I'm going to tell you I'm going to drop a ball from 2 meters. I want you to figure out how fast it's going to go. What are you going to use?
That equation.
That equation.
Oh, sorry.
You're going to use v squared equals v naught squared plus 2ad, right? That's what you're going to use. Initial velocity is
0.
0. You're going to take the square root of 2 times g times 2 meters, and you are going to get
Something.
6.26 meters per second.
Something.
Okay? I can't have the kinematic equations producing a velocity of 6.26 meters per second and the kinetic energy equations producing a velocity of like 8 meters per second. It's like, whoo, which one's right? Oh, that's tough. I don't know. Okay? Both of them have to produce the same answer. Now, an interesting thing happens.
No, ma'am.
I'm going to lift Hank up to a height of 2 meters. Okay? I'm going to lift Hank up to a height of 2 meters.
Okay.
Versus Gary the golf ball.
Oh, ma'am.
Do they both have the same amount of UG?
Yeah.
No. No.
Oh, no, 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 no.
No.
Trust me, no.
No.
Hank has a mass of 5 kilograms.
Yeah.
What? Oh,
Okay.
my bad. I thought Hank was a golf ball.
No, 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 this is Hank. It says right here. Hank. Okay, Hank. Hank has a mass of 5 kilograms.
Oh, ma'am.
So is Hank going to have more potential energy than Gary the golf ball?
Yes.
Yes. So if we were to calculate that constant here, instead of taking 0.5 kilograms, we would use 5 kilograms times 9.8 times 2, which would get me
98.
98 joules. So when Hank lands, how much kinetic energy is Hank going to have? 98 joules.
That's a lot.
That's a lot. That's a lot. Hank's a lot.
Is it?
So Hank has more kinetic energy. So is Hank going to be going faster than Gary is?
Yes.
23,000 joules.
Everyone cool with the idea that Hank is going to be going faster than Gary is because Hank has more kinetic energy?
No.
No, so help me God, no, stop, no.
Wait, what was the question?
Scared the shit out of me.
You got 22,000.
If we were to calculate the velocity, we're going to take 2 times 98 joules.
How do we enter the same values?
There is going to be more kinetic energy,
Right.
but we're also going to be dividing by 5 kilograms. And guess what? We're still going to get the exact same velocity.
I had 367
Okay.
times.
So if I were to compare these two, Hank has a lot more UG. Hank's going to land with a lot more kinetic energy. True? But
How do you get that?
he has a lot more mass.
I think you.
So he's going to land with the same kinetic energy. Excuse me, he's going to have more kinetic energy, but he's going to land with the same velocity. And that mass compensates for that. Okay? Good with that. Now, interesting. interesting thing's gonna happen.
You just made up that number, bro.
I wanna figure out
What did you get?
when Hank crosses the 1 meter mark. Okay? So here's the 1 meter mark. When Hank crosses the 1 meter mark, I want to calculate the UG, the kinetic energy, and the velocity when Hank crosses the 1 meter mark. Okay? Now, what do my UG and kinetic energy have to add up to?
9.8.
90.
9.8 joules, right?
We're not talking about
Okay? Go away. They have to add up to
9.8.
9.8 joules. So if I can find one, I can find
The other.
the other. True?
Yeah.
Cool with this.
Yes.
So which ones do you think is going to be easier to calculate at 1 meter?
Kinetic energy.
The kinetic energy or the UG?
Kinetic energy.
UG, why?
Because it's
It's a
It's
height.
mass times height.
It's just MGH, right?
Right.
So my UG is going to be 0.5 kilograms times G times 1 meter,
I didn't know you-
which is going to get me 4.9
Yeah.
joules, which is half of the total.
9.8.
Wow.
Oh, how cool is this, right? So at this point, Hank's going to have 4.9 joules of UG.
Yep.
So how much kinetic energy is he going to have?
4.9. Is it
Because
really-
at any point, my kinetic energy plus my UG has to add up to the same value. True? Everybody cool with this?
Does that mean it's linear then?
Hold on. Now, let's talk about the velocity. So, at halfway, right, at 1 meter, UG is going to be 4.9 joules. Kinetic energy is going to be 4.9 joules. Now, when Hank lands, Hank was going to be traveling 6.26 meters per second. So here's the question. Is the velocity when Hank crosses the 1 meter mark going to be half that, which is going to be 3.13 meters per second? So that's an option. Seems logical. We split it. If he lands at 6.26, halfway he should be 3.13. It's an option. So we'll call that choice B. Choice A, his velocity is actually greater than 3.13 meters per second. Okay, maybe like 4 or 5. Okay. Choice C, because he's starting slowly and falling, is going to be less than 3.13 meters per second. Okay, so here are our options. It's going to be faster than 3.13, equal to 3.13, or less than 3.13. So how many vote A is going to be faster than 3.13?
Thank you. Oh.
Okay, how about equal to 3.13? Less than 3.13. Everybody solid on that answer. Okay, how can we settle it?
Plug it in.
We know the kinetic energy, right? And according to Jackson, the velocity is 2 times my kinetic energy divided by my,
Mass.
true?
Yep.
So somebody take 2 times 4.9 joules, divide that by a mass of a half a kilogram, and then take the square root of it.
It's just 0.5. It's just 4.9.
No.
Oh, take the square root
You
of
have
it?
to take the square root.
Oh, my bad. 0.7.
What?
What? What'd you get?
4.43.
Heck no.
4.43.
No way.
Ooh, what?
Ain't no way.
Ain't no way.
Hold up.
All right, try it. Do
How
it.
do you take 4.9
Oh.
square rooted and get 4.3?
Well,
that's true.
call 4.95.
That's wrong.
No, it's not.
Call
No, that's
4.95.
That's right.
So you got 2 times 5, which is 10, right?
Yeah.
And then you're dividing by a half, which is doubling it, so it's like you're taking the square root of 20.
Oh,
that's what
okay,
I
I
was
see.
confused
Yeah, I thought the twos canceled out. So I thought it was just 4.9.
Okay?
Yeah, gotcha.
What's up, Bubba?
For feathers.
Oh, I got no feathers.
Okay.
Sorry.
It's okay, sorry to interrupt.
It's okay. You wanna sit down on a little kinetic energy lesson? Mr. Ballman sat in this room when I taught him physics many, many years ago. Flashbacks?
No, thank you. It was a good time, great experience, but
You're done?
I'm done with it.
Okay, all right. Good luck with the feathers.
Thank you, thank you.
Not a problem.
We spent the entire first month scrounging the school for feathers.
That's embarrassing.
Why are we looking for
Shh,
feathers?
don't.
Yeah,
No,
what for?
it's just don't.
No, why are we
No,
looking?
don't.
Okay.
Are they building an eagle?
Shh, no.
I'm so confused.
Okay.
Tar
Now,
feather.
here's the deal.
Indian hairdresser.
So you all were wrong,
It's not the 17th century.
okay? Y'all were wrong.
Hard feather here.
Why are you all wrong?
I knew it was
Because
wrong.
it's falling.
You're wrong because it's falling.
No, that is not English.
Wait, we're wrong that it's not less than 3.13?
Correct.
You all said it was gonna be less than 3.13.
Yeah.
It's bigger
Bigger.
than 3.13. You all voted that it was gonna be less than 3.13.
Oh, it's because kinetic energy is increasing.
No,
Okay.
that's part of it, but that's not the big picture.
The
No.
big picture.
Does velocity change as a linear function of distance, or does velocity change as a linear function of time?
Time.
Time.
Yeah.
So less time.
So what's gonna take longer to fall? The first second, the first meter, or is it gonna take longer to fall the second meter?
The first meter.
First meter,
That's right,
so it increases more.
because it takes longer to fall the first meter than it does to fall the second meter. So it's in the air longer for the first meter, right?
Oh. That's a weird to
Oh
think
my
about.
god,
I don't like that.
that is awful. That is awful.
That
That
just
just
doesn't
flips
make sense.
everything on its head.
This is like the first week.
That just doesn't make sense.
What would the position time graph look like?
Yeah, just a linear thing.
No, what, position time graph would be a quadratic
Oh,
function,
sorry, position. Okay, yeah,
right?
yeah.
So this would be like the first second, right?
Yeah.
This would be the second second. So it's going to take longer to, in the first second, right? It's going to take longer to fall the first second than it does to fall the second second. So your velocity time graph is a linear function. So since it's in the air longer in that first meter, the velocity is going to change more.
Okay, I get that, but that sucks.
Sorry, I don't make the rules. I just teach them.
We don't like that.
What?
Sorry, again, don't kill the messenger, okay?
Wait, I feel like we've had problems like this before.
What if we
And
skip the messenger and go
Probably.
straight to the
I'm
second?
confused. I'm just,
Okay,
Wait.
look at it this way. Look
Oh,
at
we
this way.
had
Look
the
at it
same
this way.
thing on the break.
Okay? You're going to drive 2 blocks in your car. Okay? You're going to drive 2 blocks.
uh-huh.
You're going to start at 0, and when you get to the end of the second block, you're going to have uniform acceleration. You're going to be speeding up the same rate. Okay? When you get to this block, you're going to be going 30 miles per hour. Okay? So what's going to take you longer to travel? Is it going to take you longer to travel the first block or the second block?
First, because you have to speed up from 0.
Right?
Yeah.
So if you have uniform acceleration, because v equals
Oh.
at,
Yeah.
so since
Okay.
it's going to take you longer to travel the first block, it's going to take you less time to travel the
Second block.
second block.
Because you're going faster going into the second block.
Yes,
Oh, okay. But you got the same acceleration.
yes,
Alright. That makes sense.
makes sense.
Yeah.
Okay, got that.
Yeah.
Good. I didn't mean to like flip you all. I was like, oh
I do feel like I've been lied to a little bit.
Yeah.
no! How not? Okay, explain to me how I have even remotely lied to you.
I feel like we've definitely had problems like that before, and it's always been like less than. Maybe not related, and then you haven't. I feel like
We've never talked about energy.
It's okay, Louis. We know it hurts. Don't blame it on Mr. Bergkamp.
reality.
Hey, don't hate the message.
It's just like logically, like
him.
watching it
We
fall
don't
doesn't.
appreciate
That's not what you would think, you know. I don't know.
Yeah.
I don't know how to explain
Okay.
Can't think through it.
Think
it.
through
Yeah,
it.
I like thinking through it. That's it.
Okay. Vanessa, pick a number between 20 and 40.
It goes here, it goes here.
31.
Where'd it go?
I don't know.
You picked a prime number.
Just that.
God, what's with the prime numbers? I've had more
love
prime
prime
numbers picked
numbers.
this year than any other year I've ever taught.
31.
I hate prime
In
numbers.
what world?
But see, I consider 5.
Vanessa
even though it's a
uses
prime
odd numbers
number,
on the
to be like
TV
an
volume.
honorary even number, if that makes sense.
She sets her volume at 17.
Yeah.
5 is an honorary even number.
Oh.
Yeah,
Vanessa
that's what I
uses
say. I
Yeah.
love
prime
five.
numbers on the TV volume.
Huh?
She sets her volume at 17.
Oh, no. See, I will only have my
No, I
TV volume
do.
on even numbers.
Exactly.
I
That's how it is.
completely
That's what
flip
it-
out. I
No, you
completely
can.
flip out if my TV volume is on an odd number.
I'll set mine to 43.
Really?
Yes, that's
Let alone a prime number. Oh,
It has to be on an odd number.
If it's
no,
on a
mine
prime
has to be on an
number,
even number.
No.
No, it has to
No.
be. This is
You're
my
weird.
television, my rules. Okay?
No,
So,
you're just wrong.
You are
Wrong
weird.
right now.
Wrong.
Alright, raise your hand if you put your volume on an even number.
I,
Okay, you guys are weird.
No, I just don't care. It's whatever
whatever.
volume I can hear it at.
No.
That's where it
Okay.
stays.
Yeah.
no, it has to.
What
Same thing with
little bother
the
word.
temperature in my house has to be an even number.
Yes.
Really?
Like 70, 72, something
69
like
is
that.
perfect
Yeah.
for me.
I don't get to touch the thermostat. I don't
You,
get
you don't have that much control.
to touch it. Hey, get off.
What?
Big inquiry, what about increments of 5?
Well, that's fine.
What do you mean?
15.
15 or 25.
I'm a
Yeah,
15er.
increments of 5 are
Okay,
good.
that's fine.
The only time I will set the only time I will do with odd numbers is like, let's say, the speed limit is 60. I always go like 7 miles per hour over. I'll set the speed limit at 67. That's the only time.
You can be at 68 and be fine.
No.
7 is safe.
I've only had one speeding ticket in my life, and that was before you all were even born.
Yeah.
It was late June of 1990. That was the last time I got a speeding
That
ticket.
must have been
And I wouldn't-
traumatic.
Well, and it was cool because I was getting ready to go to Africa, and the heck of, I wasn't even trying to speed. I was driving my mom and dad's car, and the cruise control and speedometer were off, and the guy pulled me over. And my dad was with me, and he goes, "Son, I'll pay for your speeding ticket." And I told the cop, I said, literally, like the next day I was leaving for Africa for 2.5 years. I said, "I'm literally leaving tomorrow." He goes, "Well, good. Look at it this way. It won't be on your record when you get back." I was like, "You jerk." Seriously.
Can't stand.
I was pissed.
Must
Okay.
be the end of the month or something.
So let's say that the mass of the ball we'll balance this out at 0.4 kilograms. Okay?
Did you have to go to the courthouse that day and deal with it?
Huh?
Did you have to go to the courthouse that day to deal with it?
No, Dad took care of it. He just mailed it over. Okay. So I'm going to launch the ball straight up, 31 meters per second. So I want to find the kinetic energy at the bottom. I want to find the UG at
That's all.
the top. And I want to find the kinetic and UG at 2 meters. Okay? So here's the deal. I want to throw this thing up like this. So we're defining the ground as being the reference point.
Yep.
So when I let go of it, what's the only type of energy that it has?
Kinetic.
Kinetic. So imagine here's going to be the opposite of what we just did. So we're going to start with the kinetic energy being full and UG being empty. Okay? So do I have enough information to calculate the kinetic energy of the ball?
Yes.
Yeah, so my kinetic energy is going to be 1/2.
MV squared.
So that's going to be 1/2. So somebody take 1/2 times 0.4 kilograms. Pains me to even write this. 31 meters per second squared.
192.2.
So call it 192 joules. Now, if I had doubled the velocity to 62 meters per second, what would that do to the kinetic energy? Go by a factor of 4 because it's squared. Okay? So, now if you set up your chart, and this one we're just going to put KT, UG, and the sum. Okay? So, I'm at the top. Excuse me, we'll start at the bottom. Then we got the top, and then we're going to be at 2 meters. So, since we only have kinetic energy, that's going to be 192 joules, 0, 192. So at any point, everything has to add up to
92.
192. So when that ball is at its maximum height, when it's at the top, How much kinetic energy does it have?
0.
0. We have OJ. How much UG does it have?
192.
192 joules, because we transferred all of that kinetic energy into
Potential.
potential. So everything still adds up to 192. Now that I know my UG, can I find my height?
Yes.
Yes, because UG equals
MGH.
MGH, right? So if I get H by itself, that's UG divided by
MG.
mg, which is going to give me my height. So somebody take 192 joules, divide that by 0.4 kilograms times 9.8 meters per second squared.
48.98.
So 48 point,
98.
so call it 49.0
Yeah.
meters. Okay? Pretty decent toss. Now, if you wanted to, you could work this using kinematic equations.
Wicked.
You could go v squared equals e naught squared plus 2ad. You know the initial velocity?
Yep.
Yep.
You know the final velocity?
Yep. No.
0.
Yep.
You know your acceleration?
Yep.
Guess what?
It's gonna be the same.
It's going to be the exact same. Okay?
Gotcha.
So how you work it is up to you. Now, when you're going to be dealing with it, when it crosses that 2 meter point, okay? That one you have to look at the energy perspective. So when you do that one, when that ball is crossing that 2 meter mark, okay? Start with this. When it crosses that 2 meter mark, what can you determine? Now, here's what's important. Whether that ball is going up, whether that ball is going down, or if I'm just holding that ball at 2 meters. The velocity of the ball does not impact the calculation of UG. The only thing that determines that calculation of UG is MGH. Horizontal, up, right, left, doesn't matter. Okay? So, in that situation, I can calculate my UG using MGH. So I can take the mass of 0.4 kilograms times G times 2 meters. Somebody take 0.4 times G times 2.
7.84.
7.84.
Quick.
So that's how much UG I have. So if that's how much UG I have, go away,
Not a lot.
which is going to be 7.84 joules. So I got 192 joules as my total. So how can I figure out how much kinetic energy that I'm going to have?
Subtract from 190.
Subtract them out. So somebody take 192 minus 7.84.
184.1.
180 what?
184.16.
184
Yes.
Yeah, point
point.
1.6. 2.
1.6.
Oh my god.
1.6.
184.
0.16.
1.6.
Oh, 0.16. I thought
Yeah.
you said 0.62, and I'm going,
No.
there's no way it's
I was
point.
saying 0.16.
Okay,
They
0.16.
were saying 0.62 over there.
Now,
You're probably putting in odd
if I
numbers.
know my kinetic
It's
energy
gotta be odd numbers, right?
is 184.16, now what can I do? Can I find my velocity?
Yeah.
What does it have to be less than?
31.
31. So, 2 times kinetic energy divided by mass, the square root of that gives me my velocity. So if I take 2 times 184.16 joules divided by 0.4 kilograms, you get what?
The number.
A number. Good. As opposed to like a letter or a squirrel.
Yeah.
A number less than 31.
A number less than 31, even better. We didn't create energy. That'd be cool.
The correct number.
Has nobody typed it in yet?
30.3.
What did you get?
30 point what? 30.3. Now, why hasn't it lost very much velocity?
It hasn't traveled very far.
Yeah, it has traveled 2 meters.
The total distance is.
No,
40.
time.
Well,
Did it take very long to travel those 2 meters?
no.
No, why?
Because
Because
it was going really fast.
Yes.
Okay? So when will it lose more velocity? The first 2 meters or the last 2 meters? Last 2 meters. Why?
Because it's traveling for more time.
It's going to take longer to travel the last 2 meters than it is to travel the first 2 meters. Now we're going to change it up a little bit. We're going to take that ball, and it's going to be 2 meters above the ground. Okay? Mass of 0.5 kilograms.
Still in the ocean.
I got the book problem.
But now I'm going to throw the ball.
The book one's it?
Okay?
The yellow one.
Now I'm going to throw the ball. So let's say I throw the ball up. Okay? So instead of dropping it, I'm going to throw the ball up. So when you set up your chart, we're still going to have kinetic energy, UG, and the sun. But if I throw it, what's it going to have?
Kinetic
And
potential.
potential. So because if I throw it, this is going to be a number. It's going to be a positive number. My UG is going to be a positive number. And these two numbers together are going to equal the sum. Now, if I just drop it, what's the only type of energy that it has?
Gravity. Or
Potential, gravitational potential. Now, here's what I want you to think through. From an energy perspective, if I compare the velocity that it has when I drop it versus if I throw it up in the air, is the velocity that the ball is going to have when it lands bigger when I throw it, bigger when I drop it, or it's not going to make any difference because it's still going to fall just the 2 meters?
same. I hope. Please say it's the same.
It'll be the same?
What's the question?
So I drop it
Don't do it.
versus I throw it. Is the velocity of impact going to be the same or bigger?
Bigger.
Bigger.
Bigger!
How is it not bigger?
Because it's going from a higher distance.
It's like starting up here.
No, it's not.
No.
Do it
But
again.
I'm throwing it.
Yeah, but it reaches the same top distance.
No, it doesn't. If I just drop it here.
He's saying he's throwing it from the same spot.
Okay, I got you. I thought you meant you threw it.
No.
No. That'd be very hard to do, Louis.
Okay? Now, so would you agree? Now remember, kinetic energy is a scalar quantity.
Yes.
It's not a vector quantity. So, situation number 1, I'm at a height of 2 meters, I throw it up in the air, and it falls. Does everybody agree that you're going to have more energy when it lands?
He's expired in 2015.
Seriously. Oh my God. Tell me you're not eating them.
What are those?
Okay, if you've ever had food poisoning in a third world country, you always check the dates, and your motto is, when in doubt, throw it out.
I opened them today.
I don't care. Could have opened the Dead Sea Scrolls. Guess what? Those have expired too. So,
It's gonna get the bubonic plague. It's gonna
if
get
you guys
COVID.
gone tomorrow and I have to do extra work, I'm going to be really pissed.
COVID wasn't even.
Okay? Okay.
COVID-15, bro.
Now, so visualize this. I'm here, I throw it, you all agree it lands with a higher velocity because it has more energy because it starts with UG and kinetic, and when it lands it's all kinetic. Now, what if I throw it down? Is it going to land with more velocity or less velocity?
Then what?
More.
Than if I just drop it? More. Why?
Because it has a
Starting
greater
velocity is
initial
big.
Same idea, right? It has kinetic and
potential.
potential. Think about this though. What if I throw the ball horizontally?
It's the same.
The projectile.
Because what stays in the Y is pressure.
Hold on. So if I throw it horizontally, listen to me very carefully when I ask you this question. I drop the ball, I throw the ball horizontally. Same height. In which situation does it land with more speed?
Neither.
No, the one where you throw. The
Oh,
throw.
Why?
Because it's the hypotenuse.
No,
Where it's
No.
X and Y.
no,
Wrong.
no.
It's horizontal.
Energy.
vertical.
Here's the deal.
Oh, it's got potential and kinetic.
Oh, it still has potential and kinetic.
Yeah.
Why?
Because here's the deal. Right? I'm throwing it. True? Does the direction that I throw it impact the amount of kinetic energy that it has?
No.
So if I throw it up, if I throw it down, if I throw it horizontally, if I throw it at a 45-degree angle, as long as I throw it with the same velocity, does it take off with the same kinetic energy?
Yes.
Yes. The direction that I throw it does not matter. True?
Oh.
And as long as I throw it from the same height, does it still have the same UG?
Yes.
Yes. So guess what? If I throw it from the same height, no matter which direction I throw it, as long as I throw it at the same speed, it's going to have the same amount of
Kinetic.
kinetic energy. It's going to have the same amount of UG. So when it lands, it's still going to end up with the same amount of kinetic energy, and it's going to be the same velocity.
So you're saying you didn't throw it on the dropping one?
No, if I just drop it,
So it didn't have
so
any
imagine this comparison. I drop this rubber stopper. Situation number 2, I throw that rubber stopper. Which one's going to land with more speed?
That one.
Because it has kinetic and
potential, not just
potential. If I just drop it,
It's just potential.
got the idea.
Yeah.
It still
No.
has potential when it hits the ground.
Huh? No. When it hits the ground, it has
No,
no
but it has the
potential.
potential energy until it's
Okay?
Yeah, it's going down.
All right. Okay. So stop that.
Stop it. Dude, this is a hefty assignment.
Okay.
This is hefty.
That's hefty.
It's a
I don't
hefty
like this.
assignment.
All right.
It's a conundrum.
It is. Now,
Force
let me give you a hint.
Give up.
So, when you get to question number 4, here's the setup. Archer pulls back a string, right? And it'll tell you that the average force exerted is 201 newtons. In reality, if you've ever pulled back a bow, it's actually easier at the beginning and it's more difficult at the end. So what I'm saying is that on average, the average force exerted is 201 newtons, and he's going to pull that back 1.3 meters, okay? So the first thing that you want to do is you want to sketch a force distance graph. So when you do that, you're just going to use that average force of 201 newtons
For distance.
over that distance of 1.30 meters. Okay? Now, in reality, it's going to start easier and get more difficult, which is like a spring, which is what we'll get into tomorrow. So for now, just saying, on average, this is the amount of force that's exerted over that distance. So what does the area of a force distance graph give you?
Yeah. Yes.
The joules.
Joules, otherwise known as,
Meters.
otherwise known as,
I can't work.
what work?
I
Right?
couldn't think.
So here's what I want you to visualize.
Space. What is
It's kind of like this. I'm going to take this and I'm going to pull this back, right? Am I doing work?
Yes.
Yes. I'm storing potential energy. When I let go of it, it changes into kinetic energy. So the work that I do in pulling this back
Not knuckles.
is equal to the potential energy that I store. When I let go of it, all that potential energy is going to change into kinetic energy. Now, obviously, if I just pull it back a little bit, guess what?
It's only gonna go a little bit. Oh. Ooh, Mother Nature sucks. So does McDonald's toys.
There you go.
Yeah,
Okay,
right.
there you go. So, the more work I do, the more potential energy I store, the more kinetic energy that it has.
Right.
So, what I want you to visualize on number 4 is 3 containers.
I'm looking at potential energy.
A work container, a kinetic energy container,
And a potential energy.
and an UG container. So, you're like this, you've done work.
Yeah.
You let go of it. What's going to happen to all that work when you let go of it? It's going to go to change it into kinetic energy. At the top of that flight, what's going to happen to all that kinetic energy that it has?
Turn into potential.
Keep that in mind. When you get to
8.
question number,
Eight.
Look on the back.
yeah, where'd she get 8?
We see a backside.
There's no back
I was
there.
gonna say, I don't know what you're looking at.
I'm kidding.
Europe.
I just said a number.
Here's a price.
When you get to question number 5, think through the problems that we've been working, okay? Just think through that. When you get to question number 6, and you calculate the work that's done, I was nice. I gave you the net force of the rocket. You don't have to subtract out the weight. I've given you the net force, okay? So on number 6, that is the net force. Use that in your work calculations, okay?
That's very nice.
I know. Now, when you get to the problems in the book, you're going to have a pendulum, okay? And I've given you this handy-dandy little equation that says H equals L minus L cosine theta.
Yeah.
So what that represents is the vertical change in the height of the pendulum. So L is going to be the length of the pendulum, okay? Theta is going to be that angle. Sometimes you'll see this written as L times 1 minus cosine theta. If you want to factor out an L, it's the exact same equation, okay? But what this is going to get you is the vertical height that changes as that pendulum swings up. So clearly, the farther it swings, the bigger that angle is, the greater that height. Okay? So you're going to need that on 28 and 20. Okay? That's why I have that in there. Okay? All right, I'm done.
He's done.